Okay, so this technology is that I'm going to present works for any scale, whether that is nanoscale or your hand scale or even bigger. Okay. So how to make logic gates that are universal with wires only, without transistors. Now, those gates are able to have addition, to have memory, to have state machines that are equivalent to programs. To start with, what are transistors? The things that we're replacing here. So this is a neutral wire, so the electrons do not move left or right. This is a wire that is connected by default to a minus, so there is actually a resistance, and we can actually put the plus here, and it won't actually short circuit. But if we're not connecting it to anything, it would be a minus. This is a plus, and same thing. If we do not connect it to anything, it would be a plus. The switch here would have so if it is a 1, it's gonna connect these two, and on C it's gonna be a minus. So maybe if it is a plus, this is gonna be a minus. If it is a minus, those two are separate, and this was gonna be a plus. And you can see that that's a not. And this is the function we are actually looking for from a transistor, the switch function. Okay. So to make a NAND or a NOR, we used to use two transistors like you're seeing here. Okay, so there are many other ways to make those logic gates other than transistors. So here are this is actually a thermal or biological or DNA. There are many other ways of making those logic gates other than transistors, or other ways of making transistors than semiconductors. In here, what we're going to present now is actually making them with wires only. Okay, so this is encoding a 0 as a 0, 1 and a 1 as a 1, 0. So you can see that this is a 0, 1. When we actually flip the wires, it's going to become a 1, 0. If it is 1, 0, it's going to become 0, 1. And this is a node that doesn't require an external supply of energy. Okay, so this is, as you can see, so the input from now on what follows, an input is going to be 0, A and A bar. We do not have an input by itself. We have its reverse with it. Okay, so this is 1, then its reverse is 0. If this was 0, then this reverse would be 1. So this is A and this is A bar. This is B and this is B bar. And this is out, and this is out bar. So out 1 or out 1 bar, if you like. Now, A and B would go to the out bar, then the out would be A and B. And this can be proven very fast. If you have A bar and this is B bar, and you have them in an OR, then that is equivalent to A and B. Okay, so this is an AND. Now what we're trying to make is this AND and this OR with wires only. So this is an AND with wires only. The input here, actually, and if B1 is closed, actually the signal passes, and if B2 is closed, then the signal will pass again, and it would get back to out. Here, so if we send a signal, it may get back or not back, depending on these two, whether they are both closed or not. This is an AND. Okay, now this is an OR, and we send a signal, and if B1 or B2 is closed, then the signal would get back. Now that's an OR. Now we cannot put that AND and that OR within the circuit. Okay, so this is an OR and this is an AND, and within what we just presented here. There we go. Yeah, you can see that this is an AND, this is an OR, and that's exactly what we're doing. Okay, so this is sending a signal that may get back or may not get back. But if it gets back here in one of them, then it's not getting. If it gets back in one of them, it doesn't get back to the other one. Okay. Okay, so you can see we're gonna send the signals now. Signals are sent, and depending on the switches, it's whether it's gonna return or not return. So in this case, it went returning through this way and not this way. And you can see that those switches close here or here. So this is A and this is A bar, this is B, this is B bar, and you can the switch here. If it actually closes this circuit, it opens this one, and if it closes this one, then it opens this one. Okay. Now these are can be put in series, one after the other, and if it is stable enough, meaning that there is no memory, outputs and inputs only, and on the inputs there are the buttons, everything functions fine. But if we are having memory, then we need to stabilize the energy of it, the energy supply of it, and that's where we're having these two knots. Okay. Now another memory solution is so if this is a very small resistance, this is small resistance, this is a bigger resistance, and this one would be in charge because it's closer to this line. The resistance here is smaller, and this is infinite resistance between those two. But when this closes, these two will take care of each other, and it's this resistance that's gonna this energy supply that's gonna take over here. And this can be put in a circle like that, or on a closed input to output, and that would be a clock like short circuiting or getting the output of a not backwards input. That would be an oscillator. And that's exactly what's put here, and we're trying to, this is another memory solution that doesn't use transistors. This one uses 2 transistors per memory, per bit. Okay, so what's the difference before and after this work? Well, everything is the same. It starts with software, then it's compilers, then you have in the computer architecture that actually is a structure of logic gates, and then you're having transistors, but this layer is removed and it's becoming wires only, and the chemistry and physics are the same. So photolithography or e-beam lithography, it's kind of the same for the rest of it. The only change is the removal of transistors.